All right, we're picking up right where we left off. So hopefully my cats are done fighting. And we're now going to talk about our last and really only major calculation for this chest. I guess technically you do have some calculations when you're doing these things back here where you're kind of adding and subtracting, but that I wouldn't call that like real math. Come on, guys. We got to do a little bit of real math here. So this is the only real calculation, and average atomic mass is actually the number that's on the periodic table here. You'll notice that it says atomic weight of one atom of this element in unified atomic mass units, or Dalton's DA, and the weight of 1 mole of this substance. The unified atomic mass units is not actually going to be the standard of what we're going to be dealing with in here. The AMU we used before was for one specific atom, but this number has to take into account all possible versions of an atom. If you remember, I mentioned in the last video that carbon has at least 2 different isotopes. There's carbon-12 and carbon-14. Carbon-12 is way more common, but there are carbon-14s that exist. And because of that, if you have a big chunk of carbon, you can't just assume it weighs 12 or just assume it weighs 14, because there will be random amounts of either one of those. But it's not actually completely random. We actually can base it on how common things are in the entire world or in the entire universe. So we go on what is the abundance of each of them, how common are they, and we use this as a weighted average to figure it out. So that's the reason that carbon is way close to 12, but not exactly 12. It's because there are things that are a little bit heavier isotopes of carbon. They just don't count that much, so it only raises it by a very, very small amount. And this is also why you cannot use this number when you're doing an isotope table, because this is an average. It is not a specific number for a specific atom like you're using in an isotope table. So I clicked ahead a little bit on accident a second ago, and you guys got a glimpse of it. It's a very scary looking formula, but it's actually not that bad. You're basically going to take, because it's a weighted average, you take the mass of isotope A and multiply it by the percentage that isotope A is found. Then you take and add that to the mass of isotope B times the percentage of isotope B. The dot dot dots, as I'm sure you've realized in your math classes, symbolize this could keep going and going and going and going. So this stretches on for however many isotopes you have, and then you divide all of that by 100, and you now have your average atomic mass. So the easiest way to make this kind of make sense is we're going to do an example problem. Naturally occurring copper consists of 29.17% copper 63, which has a very specific AMU this time because I'm pulling from actual numbers, 62.93 AMU, and a 30.83% copper 65, which has an atomic mass of 64.93. We're going to find the average atomic mass. So I'm going to switch to my hand cam. We're going to scoot up our paper. And our formula for average atomic mass equals isotope A, or the mass of isotope A, times its percentage, plus mass isotope B times its percentage, dot, 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 divided by 100. So isotope A is going to be our copper 63. You don't normally have to make this as clear, but I'm just trying to make sure that I'm being as thorough as possible in my explanation. We've got copper 65 is going to be our isotope B. So we're going to take the mass of copper 63, which our question says is 62.93 AMU. We're going to multiply that by its percentage, 69.17%. Then we're going to add that to our second mass. Our second mass is 64.93 times 30.83%. And then we're going to divide all of this by 100. Now, I believe I forgot my calculator at school, so we're going to go ahead and use a digital calculator online. I'm going to pull it up really quick. You can plug this into your own calculator. I didn't spare you guys. I wanted to spare you guys the embarrassment or the awkwardness of me just sitting here while I tried to find a good calculator online to plug this into. So after I plugged this in, I got 63.5 63.5466. We're going to go ahead and call that 63.55, and this would be AMU as our average atomic mass for copper. Now, one interesting thing about this, and this is a very long thing, I would expect you to just put AMU, but if we go and look on our periodic table that you probably already had pulled up at one point a second ago, and I'm going to make sure I pull that up as well. I believe the one on class actually even has this number as well. According to, if I can get a good one opened up, and no, I can't because, okay, there we go. 63.546 is what I see on the version of the periodic table that I have there. So 63.546 is the actual average atomic mass of copper. It is how we got that number from the periodic table. These are the numbers. I mentioned that at the beginning of the problem, but these here are the numbers of their mass and the percentage that they occupy in the world. So that's where we got them from. So I hope that makes sense. Your calculation could have any number of extra things up here. It doesn't just have to be 2, so make sure you remember that. But this is the only calculation that's going to be on the test. I don't really count these things up here as calculations. They're just kind of addition, subtraction. You're allowed to use a calculator on that. This is the one that really requires your logic, though. If you have any questions, please shoot me an email. Try to get into the Zoom. I mentioned last time you can send a messenger pigeon. I don't know if that's going to quite work, but I'm willing to give it a shot if you're willing to send me a messenger pigeon. Just don't let my wife see it. She would not be a fan of that. Hope you have a great day. I hope to see or hear from you soon. It's Mr. Diamond signing off.